Welcome to Module 10. We'll be doing a lot of new operations in pandas today, so we'll try to take our time. So if you're here, I assume that you're comfortable with the idea of series versus data frames in pandas, and that you have some experience with some basic table inspection. So you've run head, shape, columns, and so on. I assume that you can load a small CSV file into pandas, and you can fix obvious D-types, which was in Module 8. And I also assume you can subset rows and columns with .lock, .ilock, and Boolean masks from Module 9. By the end of this module, you should be able to explain the split, apply, combine idea behind the groupby function. You can use groupby.ag to compute summaries by group. You'll be able to use rolling or expanding windows to smooth out time series as moving averages. You'll be able to use pivot or pivot tables and melt to reshape between wide and long tables. You'll be able to describe in plain language how different grouping choices can change a decision, and you can see how this is going to be a pretty packed, although somewhat short, module. The big idea of this module is that grouping and reshaping tables is how we move between kind of raw logs of data and then the summary views that we'd often include in our outputs, in our reports, and in other communication to individuals who can make decisions, including ourselves, possibly. So the decision context or the scenario is we're going to be returning to our campus coffee stand, and we'll be helping to run it and run the data science for it. So we have a log of orders that measures the time of an order, the drink that's ordered, location. You might have a couple of locations actually across campus. The price, the size, maybe some other information too. Your manager, or maybe yourself if you're the manager, wants to decide where to schedule an extra barista, right? So maybe you want to, there's so much activity that you want to put an extra person in that particular stand. But you also care about equity. So locations that might serve mostly evening students shouldn't always have the longest lines, right? So it might be the case that you could prioritize a daytime location by adding more support, more baristas, and give them a really good experience. And just because you have less of an incentive for some reason to add extra baristas to the evening, maybe because people don't order as expensive a drink or whatever the decision will be. You have to still make sure that there's some equity going on, so you're not disadvantaging any particular group. So to answer that part, we're going to need summaries by group. We're going to need to summarize by location. We'll want to summarize maybe by hour. We don't want to have necessarily an extra barista being at the location all day long if they're only really needed at the beginning and ends of the day, for example. Maybe there's a particular drink that's very popular that requires some special training, etc. So we want to break things down instead of as high-level abstract summaries that are perhaps too vague to make any real-world decisions. We want to break things down, but still summarize so that we don't have to deal with the raw data. So we're going to practice moving from row-level logs to grouped summaries, and then from there, at least hinting towards decisions. So here's our conceptual scaffold. It's just called the split, apply, combine. So we'll start with a raw table, in this case of orders, but you can see how this generalizes to other forms of data. From that, we're going to split the data into groups, again by location, hour, and so on. On each of those groups, we're going to apply aggregations. An aggregation is sort of a mathematical operation that combines a lot of numerics together into a single statistic. So mean, sums, counts are examples of these. And then all of this will be put together into a combined summary table that's kind of not too high level, not too low level, just right for us to make decisions. Groupby is a pandas function that will tell us via pandas how to split rows. Pandas also has functions like mean, sum, and agg that will tell us what to apply. And then the result is going to be kind of a smaller summary table at the group level. So here's a small sample of coffee orders. We have 5 orders located at the Killam Library and the SUB. Sometimes people order drip coffee, sometimes you order lattes, mochas, and so on. And then you have the price of these drinks in cents, in Canadian cents. So we're going to want a row level table. We will start with this anyway. So every row is an order, as you can see here, and columns are properties of that order. So we previously described this sort of architecture of a table as a tidy table. All right, there's no grouping yet. It's just the raw logs. So here's the same data, but I just sort of mentally grouped things somewhat by location. So I sort of bubbled up some things. So here we have orders 1, 2, and 4 are all at the Killam. And here you can see orders 1, 2, and 4 have been kind of bubbled up to the top of this table, just so we've kind of organized things a little bit. So we have all of the Killam locations together, all of the sub-locations together, and so on. But then at each of these locations, we have different drinks, different prices, and so on. So the splitting step will help us group by, in this case, location. So the group by function with location, the name of the column, passed as an argument, will tell pandas, keep the rows with the same location together, and that's basically it. And so now we basically have two distinct siloed buckets. We have a Killam bucket and a sub bucket. So the third aspect of split, apply, and combine is together, apply and combine. We apply an aggregation inside of each bucket. So in this case, we want to get the total number of cents, the total income we made to get a smaller table. So something like at Killam, there's 3 sales. Each of these sales in cents are provided here in different terms. We want to add them together. That is our total price in cents. How do you do this? Well, here's the code for you, as always. We have our coffee data frame. We say group by location, Killam or sub. I only care about the price in cents column of every row. And when you gather all those together, just do a sum on that resulting bucket, and then provide that as output. That's the code. In words, we have group rows by location, then within each group, add up price cents. Within each location, add up price cents. So going forward, behind the scenes, as I have to remind you, we have like all of the code you're going to see is actually run in slide deck. So we need to import our library. So here they are. If you're running this on your own at home, you just copy this into a cell and run that in your Jupyter notebook. So here's some examples. Here's our first example. We're going to measure coffee revenue by location. So here's a tiny orders table. We have 8 orders with time, location, the drink ordered, the size, and the price. We're going to do a few things. So we talked previously when we talked about data types that, occasionally, it's more helpful to describe times not as just a string of digits and some extra characters, but as a proper date time object, so we can do arithmetic on it and so on. So we go ahead and do that. We just change the coffee order time column to, that column, but converted to date time using the built-in pandas function, pandas to date time. So again, we talked about this in an earlier module, but this takes a string, it converts it to a date time object, and then it puts that into the right row of the column we have on the left-hand side. Similarly, we can just break things down by hour. So maybe I don't care about the exact minute that something was sold in, like the difference between 9 minutes or 8 minutes, 8:05 and 8:07 is not too important, but I care that both of these sales occurred in the hour starting at 8 o'clock. So because order time is now a date time, we now have this kind of function essentially that extracts the hour from the date time, and then I'm just going to store that as a separate new column. Okay, so the result, and then coffee just basically writes out the data frame in this case, to the slide. So here I have everything written out. Order time is a bit of back and forth, but like I've converted the string to a datetime object, but when I print it out, it converts it back into a string, but it's still stored as a datetime object behind the scenes. And then over here on the right, we have like the hour that I extracted from the datetime in line 13 of the code above. A couple of things to check. You can write this down if you want, although the little pencil mark isn't here. Is each of these rows a order? If so, is there a name for this kind of table or data frame where every row is an order or an element or an observation? Are the units clear for each column? So is it obvious from every column what the units of measurement are, or not? And can you, given what we already talked about, already imagine a few ways we could group this data together? There's at least 3 different ways that we may want to group the data into little, separate silos, separate partitions, or separate chunks, right? So think about that a little bit. Think about it, check it, write it down if you can. One way to do it is by location. We talked about that earlier, so hopefully you got that one at least. So here's a little bit of detail that you probably don't need to know this level of coding just yet for this class, but we saw it earlier. So we have a data frame, we apply the groupby function, we group by location, we care about the price sense column, we do the sum, and now we can also do some sorting. So given this is still a column, I can do a sort values, and I can decide whether it's ascending or descending. In this case, I want it to be descending, so start with high values at the top, so ascending is false. And then all of this is stored in revenue by lock. One last thing I'm going to do is I'm going to divide by 100 right here, because maybe dollars is easier for you to think about in Canadian currency than cents, so that's where this last 100 divided by 100 comes from. And just in case, we round to the 2 nearest decimal points. And here we have it. So we should, this is where we actually write everything out. Location now, we have Killam and sub. We've sold $17 at Killam and $11.20 at sub. Not a huge amount, but maybe it's the summer term. So yeah, the group by function passed with one argument splits rows into one group per whatever I passed as an argument to group by, in this case location. You should go ahead and try different column names as arguments to group by to see how that works. I'm only caring about price sense at this point, so that's why it's passed in before. And then sum, we'll just add within each group. So sum over every group, or within each group, and then divide by 100. So we can do a couple of aggregations at once. So here we have coffee, we have group by location. Now I want to aggregate by a few things. I want to aggregate by the order ID and count. I want the total revenue in cents, so give me price cents and give me the sum. I want the average price cents, so again, looking at the price cents column, give me the mean. And all of this .ag will take this information, pass it to group by, run this yourself, make sure you understand what's going on here. Divided by 100 again converts the cents into dollars. And then the result of all of this is that I get a count of the unique orders. So the first element is the column name in my data frame. The second argument passed to each of these lines over here is the function I want to run on it. So I want a count of the order IDs. There are 5 unique orders at Killam, and there are 3 unique orders at sub. I want a new total revenue cents column being part of my summary aggregation. What it's saying is from the price cents, perform a sum, and then that is grouped by location. And average price cents on line 7 is down here in this column. Again, from price cents, perform the mean operation on all of the data you have in price cents there, and then that becomes a value for that group. This last line, line 11, creates a new column called average price dollars, which I specify here, and it shows up over here on the right. And then this is essentially just like the summary by lock column called average price cents divided by 100 because I care about dollars. And then the net result of all of this is I can see the total number of orders and the total number of cents, but I can also see the average price at each of these locations. And then I can kind of start, like, some very small amount of information is starting to peep out of the surface. I can at least tell that on average, people pay about 33 more cents per drink at the sub compared to at Killam. Okay, so this is a new pattern here, this ag function. So I'm still doing group by, as you saw in the code. This .ag function is this format. It takes the new column name, which you saw over here appearing in columns of my summary. The first argument is the existing column. The second argument is the aggregation function, and then that's all that I need to populate all of the cells of this summary that I'm producing. This will help keep the code readable when you have many summaries, which can occasionally occur. I would like you to definitely run this, play around with it, try removing some aggregated columns, see what happens, for example, if you remove, reset everything, run through, but remove average price cents from the aggregation before you get down to line 11. You probably already know what's going to happen, but you should run it yourself anyway. So let's get a two-dimensional summary. This code basically is what we saw earlier. We're going to group by location and hour, and then get the price cents. We're going to get the sum, like the total number of cents sold within each hour, within each location, and then we'll reset the indices. So we'll need new indices here, so you get them on the left over here. Okay, so we're still doing group by. Now, instead of passing just one column name into this open square brackets list, I have two I care about, location and hour, so they both appear. And I'm, price cents is the value or the variable that I care about summarizing, and what I want to run on that is a sum function. I'm going to add up over all of the price cents within a unique combination of location and hour. And look at this yourself, and you can confirm it. But over all of the sales done in the 8th hour of the day at Killam, we've sold $11.75 in total. Here's some additional code that takes this object, this revenue by location and hour, and then just performs a pivot. A pivot basically just flips a table around its axes. So its new index is going to be hour. Its columns are going to be location. So I want to look at hour versus location, and you just tell Python to give you indices as rows and column and locations as columns. The values, all of the numbers here are going to come from price cents, which are going to be divided by 100 because I'm going to be thinking in terms of dollars again. And that's it. This is my wide summary. So I have my wide revision summary down here at the bottom, which just printed up the table in a live fashion. So you can see a couple of things going on here. A couple of patterns are emerging. One of the various things you can observe here is that there's nothing sold in the 10th hour of the day at sub over in our data set. This might be a small point of data that you could use to say, well, maybe we don't need extra baristas to be hired and trained and brought in at the sub at 10 because we have just no indication, no evidence that there's long lineups at that hour. This code takes this wide plot. So if you care about hour versus sub versus location rather, this provides a bar chart in which the Y labels is revenue. The X labels are going to be hour of the day, right? So Y labels come from the values. The X labels come from the hours. The title is revenue by location, and everything's broken down by location. X ticks, so I didn't need to do rotation 0, but you're going to see rotation later of different types. This is just a visual thing. And then tight layout just basically is a communication to the plot to arrange things in a tight fashion. And then the result of all of this is this graph you see over here. So now we can sort of visualize something that might not have been as evident to us or as intuitive from just looking at a table of numbers. We get a figure here, which now shows, to a large extent, the story that that a table of numbers might not have communicated to our primate human brains. So one thing you can see here, which might not have been as evident in the table above, is the extent to which sales at Killam exceed the sales at Sub within the 8th hour. So there's many more people who are buying coffee at Killam than at Sub at the 8th hour of the day. This is somewhat reversed at the 9th hour of the day. So maybe if you have this extra barista, you might want to have them go to the Killam in the 8th hour and then quickly run over to the Sub to help out in the 9th hour of the day. So this grouped long table is often the easiest to compute. This pivoted table we did with the pivot operation, where we got hours versus location. This is sort of the representation that might be the most intuitive to us. And even more intuitive is a very easy transformation of this table into a visual, in this case, a bar graph. Second little example, student risk by group. So here's a tiny and tidy student table, which again we just create ourselves in this code. We're going to basically, describe all of these students individually in terms of their program and how many labs they attend, how many weekly hours of work, what their midterm was. But we're going to also flag a few of them. So we have a decision rule saying that, well, any students who got less than 60 on the midterm will be, this is a binary variable, will be stored in the at-risk column of this table over here. Okay, so here's our table. I would like you to run this yourself to get the entire table. It's going to be at risk should be off of the slide now, which I don't think I can access at the moment, but you're going to be able to access it yourself in your Jupyter notebook. Here's our raw data that we've obtained. So we want to ask a couple of scientific questions of these data. One of which might be: is there a risk rate that is different between individuals who are first-generation Canadians, first-generation residents in the country in which this university is located, versus those who are second, third, or so on generation status? So above we had that information. We had so student 1 is a first gen, student 2 is not a first gen, and so on. So we could group people by whether or not they're first generation or not, and then we can look at proportions of whether or not, to what extent the first generation students versus the not first generation students are deemed to be at risk, and see if there's any major difference between these. Okay, and in some sense, some decision makers would like there to be no difference here, right? So we'd ideally like all students on average to be more or less have the same kind of outcomes. But if it's a case that one group happens to be more at risk than the other, this might be a sign that we need to intervene somewhat at the class or university level. Okay, so anyway, here's the code. It runs. We see grouped by first generation. And looking at those who are at risk. This is kind of a way to get proportions. So the mean of a list of binary variables will basically give you the proportion of those variables that are positive, and so on. So here we have the first generation status. What proportion of these are at risk? Well, if first gen is true, so they are first generation, what is the mean value of all of the at-risk elements, so all of the ones over all of the total number of first generations? That's about 66%. Coincidentally, it doesn't have to be this way, but coincidentally, the false is about 33%. So I know this sums up to 1, but what's happening in this false column is looking at students who are not first generation. What proportion of the students who are not first generation are they at risk? So it's a separate group of people. The proportion of these non-first generation students can be anywhere from 0% to 100%, independent of the first generation students. But only about 33% of the non-first generation students are flagged as at risk according to their midterm performance. And this difference might be the flag for us that we need to do something to help, right? So maybe there's something going on that is problematic for first generation students that need to be addressed. Because this at risk column is a Boolean, this dot mean gives a proportion of true values, which I mentioned earlier. I kind of did this myself a moment ago, but I would like you to try to explain each of these numbers in plain language, right? So literally, if you want, you can rewind the video as many times as you want and listen to me explain this. But I want you to try to write down yourself what this 0.33 continuing value means, what this 0.66 value continuing value means, and see if we agree. And I would like you to also ask, is it fair to say that the first generation students are more at risk from this TOEIC sample? And it's always good, as always, to have some rationale for why you think that. So if you answered yes or no to that question, either way, you're not getting marked on this, so it's fine. But try to back up your decision in either case. So let's just kind of clean up the code a little bit. So we have our students. We group by the first generation status, but now we also look at labs attended. Maybe there's some other variable that can also explain this disparity of 33% on one hand and 66% on the other, right? Is it just first gen, or is there some other variable at play that can inform at-risk status? This is also, just a side note, an important kind of thing we want to do in data science. We don't want to just kind of, do the first thing that comes to mind, get the first result that we happen to obtain, and then run off with to the decision makers with a desire to influence behavior or outcomes. We're all scientists, certainly in this class, but in the world generally, we should all behave more like scientists. We always need to be curious. We need to ask, well, maybe this first thing I tried doesn't tell the whole story. We need to keep on scratching below the surface and see what else might pop up. Okay, we're doing things at a very simple level at this point, but I think this example sort of hammers home this idea a little bit, because now we're not just considering first generation, but we're also looking at labs attended. Okay, we had this labs attended column in our original data frame. As always, we still care about the at-risk column. A column and the data they're in, and we're still going to compute the mean values, which is more or less the proportion of individuals grouped by first generation status and labs attended. So we'll get all of the non-first generations who attended one lab, all of the non-first generation who attended two labs, and so on. I reset the index here just for convenience here on the first column, and I'll print out this table. So here we have all of our groups. Here I'm not grouping by just one variable, I'm taking two variables together, and I'm grouping by their conjugation, their combination. And so I have first generation, like I mentioned a moment ago, all of the possible combinations of first generation status and labs attended. So here are all the combinations of false, here are all the possible combinations of true within my data set. And then I take the mean. So 100% of all of the non-first generation students who only attended one lab are at risk. All of the non-first generation students who attended two labs are at risk. None of the non-first generation students who attended 3, 4, and 5 labs are at risk, and so on. We see a similar kind of story for the first generation students. So rows 5 through 9 here are all of the students for whom their first generation status is true, they're first generation students. And now I have, all the possible numbers of labs attended. This is a very small data set, so these numbers are pretty crude. But all of the first generation students who only attended 0, 1, or 3 labs are at risk. Whereas if we get to students who attend more labs, things aren't great. So after 4 labs, first generation students, half of them are at risk, whereas none of them were at risk for the non-first generation students. But by the time we have gotten to 5 labs attended for both of those groups of first generation and non-first generation, then no one's at risk in either group over there, right? So this seems to start answering the question. I'm getting ahead of myself a little bit perhaps, but it seems to answer the question that it's not just the first generation status that can explain this disparity between like the at-risk and non-at-risk populations, but there's other variables that also seem to have an effect on being at risk or not. regardless, here I have this table. I've already kind of extracted a story from it with some minor amount of effort, but I want to perform a pivot, and I want to just rearrange this this long list of summarized data into a form that might be easier for me to digest. Visually, in terms of the table, maybe it's easier for me to get a figure out of it. So I perform the pivot. My indices now are going to be the number of labs attended. That's the rows. The columns are the values of first gen over here, and all of the values, all the elements of the table are going to be my at risk, and then I just print it up on line 6. So here I have everything. I've kind of already done this, and this is a pretty weak kind of pivoting of the table I saw earlier, because there's the first table was pretty simple to look through. But we can see a couple of things here. So there's no students who are not first gen who didn't attend any labs. There are no first gen students who attended only 2 labs, and so on. But the overall story I just told is easily obtainable here. And actually, you don't have to scroll back and forth to compare row 8 with row 3 anymore, because now you can just look across what this new row 4 is and see this comparison. Okay, and you see how the story kind of unfolds over the number of labs attended. So this is a tiny table. Clearly, the more labs that you go to, the more things help. But they seem to maybe help non-first gen students a little bit more, because first gen students are still likely to be at risk for similar levels of attendance for these 4 over here. This is a small amount of data, of course, all these 100%, 0%, 50%. When numbers are that crude, that's kind of an indication that, we don't have enough data to compute really detailed summaries. So maybe I need to gather more data to tell the true story. But we have something emerging, at least preliminarily. So this is the kind of pattern we want to investigate. We won't want to stop and say, there's clearly a disparity between first gen and non-first gen students. There's often other variables, and maybe there's still some kind of strong correlation between the number of labs attended and the first gen status. I'm just making things up off the top of my head here, but maybe it's the case that first gen students might just be more likely to attend labs, and maybe that has to do with the fact that they're more comfortable sort of being in groups because they happen to be first generation students. I'm not an expert in that domain by any means, but that's one possible explanation that might explain any kind of correlation, right? So it might still be the case that first generation students are still doing better, but they're doing better because they're attending more labs. And if we just got the first generation students to show up to more labs, then the problem hopefully would be at least improved upon. So again, this is a tiny, small toy table, and because there's so little data, it's hard to have anything conclusive to say. So we have to always temper our exclamations about these things, and real decisions, how we actually intervene in the world. This is going to depend on, sorry, here we go. I'm going to zoom out again. Let's see. There we go. This is a side note, but I'm really happy, even though there's some kind of weirdnesses that occasionally happen here, I'm pretty happy how Linux supports all of these different video recordings here. What I wanted to say here at the end was, if you're going to make real decisions in the real world, you're going to have a strong amount of evidence for making them. We'll talk more about what strong evidence really means later, and I'm really excited to talk to you about that also. But for the time being, you kind of get the idea that we're not going to have a whole new expensive program before we're really sure of our conclusions. So this is the last little chunk in this lecture, in this module, on Windows, tracking changes over time. So we have rows. Imagine rows kind of are observations over time. A window will kind of take a small subset of the certain number of rows of a table, and then slowly slide down that table. It's almost like a mini table. It's almost taking a snapshot, a few rows of the table, and then looking at it in isolation with regards to the rest of the table. So we can imagine also having this kind of rigid window that we kind of pass through, and we can only see data within that window as we pass it down through the rows of our big table. So we might want to care about averages, for example. This sort of cartoon example, you didn't need to have the mermaid code here, but there it is regardless. We have a window of size 3, right? And we have a data frame of, say, hundreds of rows. And I want to kind of, get rid of slight random fluctuations that occur on a day-by-day basis and look at more, slowly evolving long-term trends. And I imagine that like a window of just 3 observations for 3 days, for example, at a time, might be enough for me to kind of smooth over all of those observations and produce one single observation. When I start at the top of the table, if I have a window of size 3, in some sense, the very, when I'm starting, the window kind of precedes the rest of the table, and I might only have the first row. So my first average that I want within that window might just be the first row of the table, right? So I take the average of the first row, not the average of 1, but the average of index 1, and that's going to be the value of my first window. I move that window down a notch. So the window is still of width 3, but now I can cover rows 1 and 2. I can take the average of those 2 elements, whatever the value I care about, prices and so on, at risk. That's my second average. I move that window down. Now I finally get 3 values, the rows 1, 2, and 3. Take the average of those. That's stored in my third kind of smoothed observation. Then I move the window down. I still have 3 observations, but now I have 2, 3, and 4, rows 2, 3, and 4. Take the average of those, and so on as I move my window gradually down the table. At every position of this window, I will look at the kind of 3 orders, or fewer, as I mentioned before, and I'm going to compute just the mean within that window, and I'm going to store it as a rolling average. Okay. Again, in case this wasn't clear, real data can fluctuate very noisily. There can be all kinds of things. Maybe there's happens to be an event one day, like one particular day at the sub, like a big conference or something like that. So maybe the number of orders we get that particular day will be like, atypically higher than usual. And I don't want to necessarily like incorporate that in my overall understanding of sales at that location, because normally there wouldn't be such a massive conference there. So by taking these averages within these windows and then smoothing things out, I kind of temper these kind of noisy, wild fluctuations. So we're going to do an example of that here. Here we're using our old coffee. We have we sort by order time, so that's why we have this. And we're making a copy of the data frame, and we're storing it in coffee sorted, a new data frame. So here we have sorted by order time. This is because we're going to be running a rolling average over time to see if there's any long-term trends over time. So we have all of our data sorted by time. We are going to create a new column. So coffee sorted, and if revenue dollars doesn't exist already, this creates it. I'm just going to grab coffee sorted, which is a column that already exists, divide by 100 to get my numbers in dollars. And this is where I implement the window. For the coffee sorted data frame, which I previously ordered, I'm going to create a new column called rolling 3 order average. And this will be defined within these round brackets. I'm going to look at coffee sorted revenue dollars, which I obtained in line 2. And now I'm going to apply a rolling average to it, or a rolling window to it. How long is the window? 3. What is the minimum number of periods? Only 1. And then within that window, am I doing a count? Am I doing a sum? Like we saw in the previous slide, I'm doing a mean, which is line 7. You can do other aggregates. In fact, when you download this code and run it yourself in your own Jupyter notebook, I welcome you to change out row 7 for other operations to see what you get. Obviously, if you were to actually run with it and you were going to change mean to like a sum, then maybe you'd consider changing the column name to rolling 3 order sum instead of average, because it is a sum, not an average, and so on. So I have this new column, rolling 3 order average, and now I just want to see what my data look like. I want to print out the order time, which I've sorted, print out the revenue dollars, which is my like exact measurement on that particular, at the time of that order, but then also get kind of a rolling 3 order average over time. Okay. Like we saw earlier, like my very first window at the top is just going to see only the first observation. So my rolling 3 order average and my actual observation is the same. The average of one measurement is that same thing. As I'd expect you to, know, like, well, you can compute this yourself. The average of 2.75 and 4.25 is going to be 3.5. So by the time I went to my second window for my second order, and I've encapsulated my first two observations, now my rolling average is a little bit different, 3.5. And the fluctuations are smoothed out to some extent, and I'm storing all of that in my new rolling three-order average column, all the way down. Now, once again, like, I'm a big fan of numbers and being specific like this, and often you still need to report your numbers in a table in many scenarios, but just for, again, our squishy human brains, sometimes it's good to put things in the form of a visual. So once again, we're going to, set our indices of our figure. We're going to set a label, set a title. All of the information is sort of stored here, so I care about revenue dollars. I'm going to plot revenue dollars, and I'm going to plot rolling three-order averages. Here's my plot function. This is a little bit different than how we were doing things in previous examples, but I just want to show you there's usually multiple ways into the same kinds of solution. Run this code. This is going to produce you this graph. And now we can see kind of long-term trends. We can also see like the actual measured revenue in dollars, which is this blue curve. And you can see it fluctuates up and down kind of drastically. But if we apply this rolling window, in this case of width 3, over my data, I end up with the orange curve, which has these kind of wilder fluctuations smoothed out a little bit. And I can see overall trends. There's not too much of a trend here, really, but we can see that, on average, we get a bit more and more of an increase in sales as the 8th hour increases, but then there's a steady drop off in the 9th hour to kind of a plateau by the 10th hour. Okay, so you can go ahead. I want you to go ahead and maybe play around with this. You can go here and change the window to 2, to 4, to 5, and see how the graphs change. Hopefully, you're going to see that larger windows, like changing 3 to 4 or 5, for example, will produce smoother curves, but it'll also be slower to react to sudden shifts in the trend. So the longer the window, in some sense, the longer it's going to take your graph to recover to like what the new normal is, so to speak. Here, the window size is rows and not minutes here. Like previously, we talked about time. We did order by time, but the result is individual rows in our data frame. So there's just a bit of a catch. We're not, the window is not kind of being rolled over like time specifically. It's still a window that takes in a number of rows of observations in our data frame, right? There's a subtle difference, but it matters. In real time series, like it matters because of this, right? In real time series, you might, want to understand temporal dynamics a little bit better. So you might not want to kind of have a window that only looks at individual orders and have that rigid, because the number of orders can rise and fall drastically over time. So you might try an average over like hours or quarters of hours or days even. So how we actually choose these windows, how we'd actually write this function in different scenarios in practice might be a little bit different. And for now, we're going to leave it as it is, but the same kind of idea applies. It's just that the window will have a different number of rows in the data, but it'll have the same number of minutes, for example, in time. So a bit of reshaping before we finally wrap up. Here's our wide grades table, okay, produced for this code. We have 3 students. These are their IDs. These are not their names necessarily. And then we have their performance on 3 quizzes. Okay, everything's like 7, 8, 9, 10s. Nothing really seems to be jumping out at us just yet. This melt function, which you can learn about more at this link, kind of unpivots a data frame from wide to long. And it can optionally leave the identifiers set. So this can be helpful sometimes if you want to sort of massage a data frame into a format where it's like more columns are what we call identifier variables, like ID vars here, and we can use those for grouping. You want to unpivot, group together variables together, and then perform some kind of aggregate functions. Maybe you want to separate out value variables to make them unpivoted, but rather than talk about it, let's just look at it. So we have grades wide, which I defined on the previous slide. Here we melt it. We have the identification variables being just student. The variable names are going to be assessment, and then the value names are going to be their scores. And then I want to print that out, okay? So going up a slide, here we have a table where I can kind of look at things at a student by student basis. For some other reason, I want to unpivot, kind of put things back into a format that might be more common for a tidy table in a raw data frame. So melting is sort of like unpivoting. And now this is a bit harder to kind of visualize what's going on. Like before I could see how a student is doing at a glance. And now here I have a combination of students and assessments. And then the story, for the moment, seems to be harder to differentiate. But like we saw a moment ago, sometimes we want to run operations on a table in this format. So this sort of makes it easier for that kind of eventuality. So here's our long format after melt. We have our students, our assessments, we have our scores. We have our wide format after a pivot. So we have, we can pivot, we get assessments versus the students. We have the same information. We're just kind of rearranging things. It's in some sense it's rearranging the deck chairs, but not really because we're doing fine. These, now rows are assessments, columns are students. I'm still getting information at a glance, but here I'm getting kind of more information at like the quiz level. I can kind of see across rows how performance changes over time. I mean, technically, if you pivot things the other way, you could do the same thing, but regardless, sometimes where we need to write things out with certain rows and certain columns. So this is how you do it with melts and pivots. So we have our pivoted summary, we have quizzes, we have our students, again, obtained from this code. Our wide format can be convenient for some modeling and simple plotting. Our long format can be often nicer for a group by. So here long, I might have previously called tidy. So faceted plots joining with metadata, melt, pivot table. These are all functions that help us, kind of transform data into one form or another according to what we need. So that's it. I would like you to answer these quiz questions for Module 10. There is one page of it. And before you come to class, complete those quick checks, bring them in, skim the deck again, pick out some examples of groupby, .ag, determine which ones you could reuse, play around with them a little bit, and try using them in different contexts with different things you're measuring. Identify an example of pivoting and melting that you want to try, either in a project or just for fun, and play around with it a little bit, just see how things are behaving. Again, I can't stress this enough. Like you can watch this video as many times as you want, and you can watch it full screen with no other distractions on, but and focus entirely, which I imagine all of you are doing anyway. But regardless, nothing really beats hands-on manipulation, hands-on practice. So, like when I'm saying please play around and copy them and run the code, that's not just I'm not just saying that. I really hope you do that. I'd like to bring a question about a step that still feels like magic to class. And then, when I come around, we'll discuss the code together and work out any problems you're still having. I'm looking forward to that, and I'm also looking forward to the next module. See you then.